just let me quickly, recap what happened in the last two talks. So the goal was to at least sketch and hopefully in some detail, some aspects of the proofs of global stability for the trivial solution of these three equations. And already just these three tools, energy estimates, weighted Sobolev inequalities, and a bootstrap argument is basically enough for the first equation. For the second equation, you wanted to move down from a cubic nonlinearity to a quadratic one. Unfortunately, the result isn't always true. And so you needed some additional structure. What you basically needed is that the derivative or the nonlinearity would sort of see the difference between good and bad derivatives. Good derivatives being derivatives tangential to outgoing null cones, so level sets of U. And the condition we needed on Q was basically that there was no bad derivative squared, right? And this was the null condition. Basically, just using weighted Sobolev inequalities, you could see that good derivatives are better in L infinity. But you also needed to see that they were better in L2, and that's what characteristic energy estimates did. All right, so now we're sort of moving on to this last equation. And I'm basically just going to try to mimic the proof of 2 step by step and see what breaks and what you sort of have to change. And hopefully we can figure something out to deal with the things that come up along the way. So the first thing I have to tell you is, what do you assume about these coefficients, A, mu, and B? So in a bunch of problems, you might have some kind of stationary background solution, and you're trying to understand the stability of that. In such a situation, something like this might arise. And then these coefficients, A, mu, and B, would in some sense be time independent. So I'm just going to assume that dt of A mu is equal to 0, and dtv is equal to 0. So they just depend on the spatial coordinates. In general, this could also be sort of extremely difficult. So, just what's the simplest setting that fits into this framework? It's where you assume also that A mu and B are smooth. Compactly supported. In, say, the unit ball. And moreover, they're small. And I'll measure their smallness with some parameter delta. So what I sort of think is that A mu and a bunch of its derivatives. So in CK plus V in CK is less than or equal to some parameter delta. And I'll allow myself to sort of take this as a smallness parameter. So in a lot of problems, you don't have this kind of structure, but this is just the simplest setting you could imagine like that. And some of the things that you already have to think about in order to deal, some of the things you already have to deal with and think about in this case, at least part of the idea generalizes to other situations. And so sort of just understanding that's the goal. Okay. So are there questions about the setting? Okay. So No, sorry, I should have said this. I mean, you can allow for that also, but let's even think something simpler here. Thank you. Good question. So A mu and B are fixed. So they do not, so fixed functions of the spatial variables, and I'll just call that x, okay? This sort of what we'll go through is more general, and a lot of these ideas work in more general situations, but just keep it simple. All right? Okay, so in the proofs of the other two statements, one of the main things you had to do is to do an energy estimate. And what you always did is you sort of looked at the linear part of the equation, did an energy estimate with that, and then tried to treat this nonlinearity perturbatively and say that it doesn't change the energy too much. So let's first just start to see what happens when you try to do an energy estimate for this. You can either do this this sort of more sort of basic way that you would see in an introductory PDE course. I also talked last time how you can do this with the energy momentum tensor. I'll just write this as saying you multiply by dt phi, integrate by parts, or you use the energy momentum tensor, and you'll have to use the equation at some point. You know. And what you end up getting up to factors of 2, which I'm ignoring, is something like this. Also up to negative signs, by the way. But it doesn't matter. And in the linear case, so if Q is 0, there would be no other source term. So this is just sort of right now the linear energy estimate. Because remember, if we can get linear energy estimates, we have a strategy to deal with this perturbatively, right? So I'm ignoring the nonlinearity for now. And this is just equal to initial data. Right? And if you compute this carefully, you'll see that I have a bunch of signs wrong and I'm missing factors of 1/2. It doesn't matter. It schematically looks like this. All right, so already you have a couple problems. The first problem is, oh, and sorry, I missed something. But you know, all of this is data, so it sort of doesn't matter. You can just reasonable assumptions on data can always deal with this stuff. But already you have a couple problems. Like the first problem, actually, let me ignore this for now. The first problem is this. What you can see by looking at this is that the best case scenario for you would be if V had a certain sign, and that sign was such that this and this have the same sign. If you had that, this V actually seems to help you, because this phi squared term usually isn't in the energy estimate. But if it had the good sign, all of a sudden it is. In fact, if you have that assumption, and if the A mu just wasn't here, you would have a very nice energy estimate already. That's the point I'm trying to make. But I don't want to assume a sign on V. And I also don't want to assume this is 0. So what you might worry is that this conspires to really make this quantity that you're controlling much weaker than it otherwise would be. That's the first issue. So the first issue is the effect of V on the energy. And the second issue is this right here. Very, very, very naively, think about what this looks like. This is a mu times something quadratic, which is sort of exactly what arises in your energy. If you squint, what you're worried about is that this sort of looks something like this. E of S, meaning the energy at time S, plus the integral, well, what you'd really be worried about is minus the integral from 0 to S of E of T dt is equal to this looks bad because this sort of looks like exponential growth. This is sort of the worst case behavior. Of course, it doesn't. There's something here that makes that very different. For example, the A mu are compactly supported in space. But still, you have to deal with this somehow. All right? All right, so but first, are there questions about why these are potential issues? So first, let's deal with this first issue. Why is this okay? So just sort of starting with issue 1. Why is the potential okay? You should just think to yourself, what would a function look like where this would sort of start to overwhelm this? Is that possible? And what you sort of see is that because the potential is defined to be small, or is assumed to be small and compactly supported, it sort of seems impossible for this to be large unless this is also very large. The reason for this is because phi squared sort of on the unit, like if you have energy, say 1, phi squared would have to be of size roughly 1 over delta, or 1 over square root of delta on the unit ball in order to make this term comparable to this, right? But phi is a function which vanishes at infinity. So if it's very large point-wise in a certain region, like of size 1 over square root of delta, that kind of tells you that the first derivative by some kind of mean value theorem ought to be kind of large in some region as well. So it seems like if you try to make this large enough to compete with something that has, you know, this of size 1, it seems like you might need this to be large. All right? So this is how you might think that this is okay. One way you might think that this is okay. And let me actually provide a proof that this is okay, because this is sort of an important this kind of issue arises frequently. The key thing that you're leveraging is 1, this thing is small, V is small, and 2, it's really localized. So what I'm actually going to use is something called a Hardy inequality. And this is sort of overkill, but nonetheless, let me do that. So first, observe the following. In absolute value, this is certainly true. This is because the potential V is compactly supported, right? And it's less than or equal to delta point-wise. So certainly this is true. So what I can say is that this integral here at any time slice, doesn't matter. I won't even write down where you're integrating. This should be less than or equal to, up to some constant, delta times this integral. Right? All right, so I chose this r to the -2 for sort of a specific reason, because it's sort of going to give me what I want. And all I'm going to do now is essentially give you the proof of, one part of what's usually called a Hardy inequality. It's a more general statement, but so I can write this in polar coordinates. And you integrate over the spheres, 0 to infinity. This cancels with the volume form, so I'll just erase it. So it just looks like this. Where by d omega, I mean you're integrating with respect to the surface measure on the sphere. Just a sec. I think I might be setting up the wrong Hardy inequality. Just sorry, one second. So. It's okay. All right, sorry. I'm going to write it like this. Sorry about that. Okay. Now, I can simply write this as follows. With a negative sign. And I can integrate this by parts. The term at infinity will vanish because phi is sort of assumed to vanish at infinity. And you can just check that the boundary term at r equals 0 will vanish, because even though there's a negative power of r here, phi should be smooth, and there are more powers of r here. So when you integrate by parts, this ends up being equal to. Please check if I make a mistake at the board, because I have a friend who told me that his biggest fear in life was doing linear algebra in public. And I sort of feel like that about just computing in public in general. So please stop me if I make a mistake, because when I reach the punchline, it would be bad. Okay. And so now the point is, just an application of Holder's inequality will tell you that this is less than or equal to delta. Less than or equal to delta b squared. So b times r to the -1 lx2 times dr of r phi r to the -1 lx2. And this is with respect to the standard volume form, like r squared dr d omega. And this is exactly what you have on the left-hand side. This is sort of this quantity here squared. So altogether, what you've sort of shown is that phi r to the -1 lx2 is less than or equal to. Oh, and I dropped it to 2. All right. And if you expand this out, what is this quantity? Just write out this integral. And this is sort of exactly what you have in your energy, right? So this doesn't quite bound you directly by the energy, but I did it this way because I'm, soon going to just start computing directly with R phi instead because it makes computations later easier. So I wanted to sort of, do it this way for now. I leave it to you as an exercise to use some kind of Hardy type argument to control these things, all right? If you wanted to truly get the energy, I leave it as another exercise to not do this. Instead, write this as the integral of just phi squared, and then just use the fact that 1 is a derivative of r and integrate that by parts. Okay? Make sense? If you did that, you would actually immediately get the Hardy inequality you want to use. I wanted to run through this again because I'm going to start computing with R phi directly. Okay, so if you unravel all of this, what you should think is true is that the so let's look at this term here. What you have is the integral over sigma s of d phi squared dx. The constant here is about 1 plus integral sigma s v phi squared dx. And this Hardy inequality, plus using the fact that v is pointwise small, sort of tells you that this thing here is less than or equal to delta times the integral of d phi squared. Right? So thus, I can say that this combination here bounds just something with a slightly worse constant here, like maybe let's say 1/2. Right? So this is nice because this tells you that this new term, which arises in your energy estimate, at least it doesn't make your energy weaker if you're allowed to lose a small constant. It's basically just as strong. Make sense? Okay, so now there's another problem, which is sort of in reality kind of more serious, and it's this one here. So here's another exercise for you. If you drop the compact support assumption, just make this actually look like exponential growth. Like really make sort of that second problem really seem like it should be true. And anyway, play around with it. Maybe on a compact manifold, something like that. All right. So for the second issue, you really have to take, you really have to use the fact that this A mu is localized. Let me sort of try to give an idea of why this might be helpful. If you're familiar with geometric optics, it just says that sort of solutions of the wave equation ought to travel along rays. And this is sort of always true along null rays specifically. And this is sort of always true, or in a lot of generality, in a high frequency limit. It turns out that for the constant coefficient wave operator, it's sort of always true because the coefficients are constant. So you have some nice sort of scale invariance. And there are a lot of ways to make that rigorous. But what that should make you think is if you look just sort of at the space-time cylinder, or the sort of the region bounded by the space-time cylinder, r is less than or equal to 1. This is the only region where things are actually different from the cases we've already studied, right? outside of the region R is less than or equal to 1, the operator in question is literally just the flat wave operator. So this leads you to have the following hope. Any ray, any null ray, can only live in this cylinder for time about 1. Again, if you're in units where the speed of light is 1, any ray, any null ray, after it enters the cylinder has to exit it within, let's say, time 10, something like that. This is just because, you know, essentially because these lateral walls are time-like. All right? So what this means is that if you think that waves just involve stuff propagating along null rays, all the bad stuff can only happen for time like 1. That's not so bad. If you grow exponentially for time 1, that's like multiplying yourself by 2, something, you know, it's not that bad. And then after you go through that bad behavior, you're back in the region where you really understand how things happen. So the strategy is going to be to sort of try to throw away a compact set. And by compact, I mean spatially compact. So this is sort of what we want to do. We want to prove some estimate that lets us just forget about a compact set. And the thing that lets you do this is integrated local energy decay. This is also called Morowitz estimate because sort of the first version of this is due to Morowitz. So let me start to compute for you this integrated local energy decay statement. And it turns out that this is purely a Minkowski space computation. This is sort of all cooked up so that if you do the Minkowski space computation, everything else can be treated perturbatively. Similar to how in this case here, the potential could just be treated perturbatively. So for a variety of reasons, I sort of don't really have time to motivate this better, but you can think at some level that this is motivated by some of the explicit computations I said you could do in spherical symmetry. You looked at box phi, multiplied it by r, and in spherical symmetry, it looked like this. And that was really convenient. I'm just going to start computing that way for now because it makes the computations nicer. And I don't have, you know, it would take too long to do it otherwise and to motivate this better. But you can already see that sort of in large R, you should think that this is perturbative. Because this Laplacian not slash, this is the Laplacian on the unit sphere. And I leave it as an exercise, that Laplacian not slash, so this thing here, is just the sum over the rotation vector field squared. Where I'll remind you the rotation vector fields are things like this. And again, we already saw that you can use these vector fields to great success. So we hope that this is sort of okay for that reason. All right. So so here's how the integrated local energy decay statement goes, or the Morowitz estimate. This is sort of the integrated local energy decay. You can think that this is sort of energy estimates part 3. So last time I mentioned how you can play around with sort of the surfaces on which you do energy estimates. Now I'm not going to play around with that surface. I'm going to do some kind of integration by parts between 2 constant time slices. But now I'm playing around with the V, the multiplier. It's not going to be partial T anymore. What I'm going to do is I'm going to essentially use partial R as a multiplier. After you do this renormalization, what you should really think is I'm using partial R of R phi as a multiplier. And then the volume form is hidden sort of with phi. All right. So you're integrating between time 0 and time s. Integrating R from 0 to infinity, and integrating over the sphere. So again, note that the geometric volume form on R3 has an R squared here. You can sort of think that I've paired that with the unknown variable itself. Okay, so I'm going a bit slower than anticipated. So here's what. All right, let me just tell you the kinds of terms that appear. So when you integrate this thing by parts, I think you can see that sort of you'll get integrals in on constant time slices that look something like this. So now you're sort of seeing the fact that partial R is different than partial T. Because this doesn't seem like it should have a sign. This is partial T of phi times partial R of phi. It no longer has a sign, right? But if you think about it, this should be controlled by the energy. So just like before, how for the potential term, I was able to sort of absorb it into the energy in this way. What I sort of think is if I take this estimate and I add 10 times the energy estimate, something like this. If I add 10 times the energy estimate, all these constants are just multiplied by 10. So this becomes a 5. And that will then allow me to absorb this. Does everyone see this? It's sort of completely analogous way to sort of what's done there. The more interesting things happen with these two terms. This term here, you now actually get a boundary term at R equals 0. So this term here, you get an integral over R equals 0 of just phi squared, which is amusing. And the final thing that can happen is this partial R can hit this R to the -2 when you're integrating by parts. No other boundary terms show up. But the great thing is that this, when the partial R hits this R to the -2, you can check that it gives you something with the same sign as this. So it's sort of all good. So this is. Okay. So this is very nice. Using partial r as a as a multiplier gives you something that has a space-time sign. And it gives you terms on the boundary, which are usually the things that you think of as being, you know, the things you want, the energies. But now you're treating that as an error, which you control with a regular energy estimate. So here's what I'd like to do. If I sort of unravel this, what I can see is that this sort of looks like first derivatives of phi written in terms of vector fields that have components about 1 times 1 over r. That's what this looks like. So once again, because I have smallness in this a mu, if it happened to be that all of these derivatives here are angular instead, this term, which has a good sign, would completely dominate this one. And so once again, I could sort of absorb this, just in a similar way as was done with the potential up there. All right. Unfortunately, the terms aren't all angular, but this gives you an idea to sort of play around with partial r. And here's sort of what you can do. You can instead use something like this. As a multiplier. Now let's just track sort of the different things that occur with this compared to the other case. The boundary terms will look similar, and you can once again hope to control that with the energy. But now the point is, when you're integrating by parts, because there's a partial r here on the multiplier, you'll always have a situation where you integrate by parts and the partial r falls on this. And it will consistently have the same sign. The reason for that is because for the partial t squared term, you have to integrate by parts twice. For the partial r squared term, you just integrate by parts once. So the difference in the number of times you integrate by parts takes account for the sign difference, because every time you integrate by parts, you pick the negative sign, right? So in other words, the terms this generates will have the same sign, which is sort of exactly what you want. And so, you know, exercise is do this integration by parts. And what you end up getting is something like this. So it's yeah. All right. So there's still a little something to do, which is sort of annoying. And that is that this term here could have a partial r term. And this is saying that you don't control the space-time, this sort of space-time L2 norm of partial r phi. You control it of partial r of r phi. Once again, this is all cooked up so that's sort of a Hardy inequality. In fact, exactly the Hardy inequality that I did originally will sort of tell you that phi squared is controlled by partial r of r phi squared. And so expanding this out in sort of the way that I had before, you can see that sort of everything's consistent with actually controlling this term. So if you'd like, you also control this, a term like this, with the r outside. That's the upshot. All right, so this is great. This basically tells you that if you take 10 times partial t as a multiplier, and you add this Morowitz estimate, which comes from using like partial r and this thing as a multiplier, add them together, it looks like you get an energy estimate. And all of these bad terms are absorbable here into the integrated local energy decay statement. So this really is sort of taking advantage of this fact that the A mu's, this sort of perturbation of the box operator, only occurs in a spatially compact set. Questions about this? Yeah. Yeah. Yeah, right. Yeah. There you can, well, yeah, even I was going to write something about that just in a second. But any other questions? All right. I wanted to say a bit more about how you could motivate this multiplier. I'll just tell you that one way to think about it is you're trying to sort of track, energy moving away from a cylinder. And if you think in spherical symmetry, one funny thing is that the wave equation is symmetric, meaning you can interchange space and time, and you can still sort of solve. So this is kind of like doing an energy estimate sideways. And that's sort of what you're trying to track. It's sort of stuff moving sideways. An exercise is to think about that. And, yeah, anyway, all right. But what I actually want to talk about is just to sort of tell you the punchline. This step, and this step are sort of all exact. Nothing is messed with here. We just saw that you had to modify energy estimates by incorporating integrated local energy decay. This step is also messed with, though. It doesn't work so well. And here's the reason why. This sort of all works very nicely for just a basic energy estimate without commutation, but we also have to commute the equation we saw and take advantage of weighted Sobolev inequalities. So the issue with this is that you can sort of check that you've lost access to boosts. This is to say, boosts are things like TDX plus XDT. And just by the assumptions we have on the coefficients, when you commute with this, if that thing falls on this coefficient, you basically pick up a factor of t potentially, and that's bad. I mean, this whole discussion was assuming this thing was perturbative in some way, and then it sort of starts to grow, and that doesn't look perturbative at all. So the only things that we can sort of hope to use in this setting are scaling and rotations. It turns out that you can make things work just with scaling and rotations, but I'll instead try to show sort of another approach that sort of is extremely useful in a bunch of situations. And it gives you replacements for a lot of stuff that's lost when you don't have boosts. And so this is 7. These are R to the P estimates. So these R to the P estimates, they're weighted energies. So once again, like I said before, you can play around with the surfaces on which you're doing energy estimates. You can also play around with the vector field. I've only used unweighted vector fields now as multipliers. We saw that using weighted vector fields was nice for commutators. So now I'm going to use weighted multipliers. So one other thing to note is if you think in terms of the energy momentum tensor, when you compute the divergence, you can see that using killing vector fields or conformal killing vector fields is very nice. And the reason for that is because you end up contracting the energy momentum tensor, which is symmetric, with essentially the geometric gradient of the vector field. So, and you know, the symmetric part of the geometric gradient of the vector field, if that vanishes, it's exactly a killing vector field. So one thing to look for, just like was the case with commutators, is to look for killing fields or conformal killing fields. This is sort of a bit different. There's sort of this renormalization we're taking into account by first multiplying through by R. And I'm really not going to have enough time to say as much as I wanted about this. So let me just start computing a bit. So, I wrote down the wave equation in spherical symmetry. And in terms of these null vector fields, L and L bar, you can rewrite it as follows. So this is R box phi. So let's say you solve the homogeneous wave equation. Let's just hit 0. The R to the P estimates are essentially the following. You just use R to the P, L of R phi as a multiplier. And you see for what P, this gives you something useful. And, so multiply by this, integrate by parts, see what happens. You can see that sort of the nice range is P between 0 and 2. So let me just write down what it is you end up getting. And you can compute this yourself. You'll end up getting, so let's do the integration by parts, say, in a region that looks like this. So this is t equals 0, where you have data. And I'll integrate by parts between this and let's say a cone u equals constant. If you do this, you'll end up getting a flux on this cone, which looks like this. Something like this. You'll also get a space-time integral in this region omega, which looks like this. Oh, sorry, this should be squared. And then this will be just equal to, you know, data. So I wasn't precise about constants here. As you can sort of guess, when you integrate by parts, there are terms where derivatives fall on R. So there should really be constants here which depend on P. And the reason P equals 2 is a barrier is because it turns out that the constant here vanishes exactly when P is equal to 2. And it starts to have the bad sign if you go above that. All right. So let me, in the last like 5 minutes, let me just tell you what this gives you. And then I'll try to motivate the multiplier a bit. I probably won't have time for that. And then finally, I'll try to give you references for all this stuff, you know, that I've done in the 3 lectures. So the first thing is this is giving you sort of weighted control over several derivatives, which if you think about it, is very similar to what commuting with weighted vector fields did. Because when you do an energy estimate after commuting with weighted vector fields, you have weighted things, right, that you're controlling. So this is sort of giving you something similar. It's just that the weight comes from the multiplier instead of the commutator. So you can leverage that. Another thing is this gives you sort of a very clean way of seeing how good derivatives are better. Just like before, how using characteristic energy estimates did. So here's an exercise. Prove that these kinds of fluxes aren't bounded if this is a bad derivative. Just as an example to see that this really is telling you the difference between good and bad derivatives. All right. Okay, I don't really have time to try to motivate the multiplier some. You can ask me later if you want to see. Let me just so let me just give you references for these things. So the first thing is, I think the main thing I wanted to do is to show at least some of these tools, some of the key computations in some detail in the simplest setting. I'm sorry, I didn't really get to say much about this, but it's very, very important. These R to the P estimates, by the way, are due to de Fermos and Rodniansky. But these things come up a bunch, and in particular, a bunch of sort of these simple ideas. For example, trying to ignore a compact set. That's a common strategy to do, even if the mechanics of being able to ignore that compact set in some sense are much harder than what I showed here. So I would sort of say that sort of original sources for a bunch of this stuff is there are a bunch of papers by Kleinerman. There's some by Christodoulou. Like I said, the first sort of integrated local energy decay statement comes from Morowitz. I have no idea where bootstraps originated. I don't even know if it would be possible for someone to track down. You know, it's everywhere. For null condition, again, look at these sort of original papers by Kleinerman and Christodoulou for the original source. And then sort of, and for R to the P estimates, it's a paper by de Fermos. De Fermos and Rodniansky. And for sort of lecture notes or more pedagogical things that cover this, my, Jonathan has lecture notes, which I think are amazing. So they're on his website. There's also a book by Sog. And there are a couple books by Alanak. I think now there are getting to be more nice lecture notes that cover these things, like Dejan Gajic also has some lecture notes. Maybe Gustav does also, Gustav Holzickel. So yeah, it's yeah, anyway, I'll stop here. So you need you still need weighted Sobolev inequalities, but that inequality, for example, this inequality or the one that I showed before, Kleinerman's Sobolev inequality, that used boosts, which you don't have anymore. So you have to get weighted things in different ways, and you don't. Yeah, it's a bit different. But there still are weighted Sobolev inequalities, definitely. Sorry. Yeah, and so so one thing that I didn't have at all time to say, which I meant to say, is how can you remember that Kleinerman's Sobolev inequality and a bunch of other stuff we talked about before was decay away from u equals 0. So there's a way to use these R to the P estimates to get that. I didn't talk about that at all, but that's very important. Yeah. Yeah, because the like with just the regular wave operator, the point is sort of when you commute with a boost, you get something that solves basically the same wave equation with somewhat different looking nonlinear errors. If you commute this with a boost, you still get something of the same form, but the properties of the coefficients change drastically. In particular, here there's the assumption that they're bounded by delta. And if you just sort of compute what that would mean, now these coefficients would be bounded by delta times t, which is no longer perturbative for large t.